Welcome to lesson 9 from topology. We're going to talk about closed sets and metric spaces. I'll define a few concepts leading up to the definition of a closed set. I'll give a few examples, and then we'll talk a little bit about the relationship between closed and open sets, which I alluded to in the previous lesson, but we'll get into a little bit more detail in this lesson here. Before we define closed sets, we need a couple of concepts. The first one is something called adherent. Let's talk about that. So we have for a subset Y of a metric space X, a point X, little x and X is adherent to Y if for every open ball about X, the intersection with Y is not empty. I have an example here on the right. Let's say that X is a two-dimensional Euclidean space and Y is this gray squiggly thing without its boundary. I put it here as dotted lines, a dotted curve. So this point here, and it is a point, I couldn't make it any smaller using PowerPoint, but this point here is adherent. Even though it's not in Y, no matter how small a ball you put around this point, you're going to include some points from Y. So that is inherent. That's why we define this term here. You can have points that are very close to a set, so close that no matter what ball you put around it, it includes points from the set, in which case we call the point adherent. Related to adherent is something called closure. The closure of a set Y, represented as Y with a bar above it, is a set of all points in the enclosing metric space X that are adherent to Y. So by definition, each point of Y is adherent to Y, and Y is a subset of its closure. Because if you take a point, say in Y, no matter what open ball you put around it, I'm just pointing here to our example, no matter what open ball you put around it, you're going to get at least that point, and in this case here other points, so the intersection would not be empty in that case. So all the points in the set are adherent to the set. I have a few examples here. This first example is similar to our example here, our rough example. So if we take R2 as our metric space, the Euclidean space, two-dimensional Euclidean space, and we take a circle but not its boundary, so the interior of a circle but not its boundary, then each point in this set A is adherent to A, and in addition, the points on the boundary of the circle are also adherent to A. So the closure of A is A itself, and then we just add in its boundary. So we put in a less than or equal to here, and that gives us the closure of A. We have a slightly different example here. If we take B equals the infinite set, 1, 1/2, 1/3, 1/4, so on, each set in B, each point in B is adherent to B. That's always true, as we noted up here. The set is always a subset of its closure. But we also have another point that's inherent to B, and that's zeros. Because this sequence here is converging to zero, no matter how small an open ball you put about zero, you're going to include some points from B. And so 0 is also inherent to B, and the closure of B is B itself, union with, this means union here, union with the point 0. So one more example, or actually two more examples. If we take this set here, inside of the one-dimensional Euclidean space, so just on the number line, we take the points from 0 to 1, including 0 but not including 1, and then the points from 1 to 2, not including 1, but including 2. The closure of that is all the points in these two, the union of these two sets, plus 1, which is the additional point that we add for the closure, and that so the closure is just the closed interval from 0 to 2. And the second example here is we can take the union of the interval from 0 to 1, including 0, not including 1, and then going from 2 to 3, but not including 2, but including 3. And then the closure, we just have to add 1 to this and 2 to this, and this is our closure. We can now define closed based on our previous definition. So subset Y of a metric space is defined to be closed if the subset equals its closure. So in other words, it contains all its points that are adherent to it. Just going back to our examples from the previous slide, which I've recopied here, we can see that A is not closed since it doesn't equal its closure, but the closure of A is closed. That's always true. The closure of a set is always closed. We'll prove that later. And again, B is not closed because it doesn't contain all the points that are adherent to it, but the closure of B is a closed set. And then for C and D, we have the same situation. C is not closed, but it's 0 to 2 is closed, and D is not closed, but then this union here is a closed set. And just going back to our concept of open, set A is open, but B, C, and D are not open. In fact, C and D are neither open nor closed. So open and closed are not opposite concepts. If something is not open, it doesn't mean it's closed, and vice versa. There is a relationship, and I'll talk about that in this lesson, but we'll get to that in a few minutes. A few more examples. We have this equation here, all the points satisfying x minus 1 squared plus y minus 5 squared less than or equal to 3 is a closed disk, and in fact it's a closed set. The radius, it's a circle of radius 3, and the center is 1, 5. A single point in 3 space, Euclidean 3 space, is a closed set. And then this set here, where we added in 0, basically the point to which this sequence converges, we've added that in, and so this is now a closed set. We have another term here, something called a limit point. It's sort of like an adherent point, but not exactly, and I'll give you an example in a minute. Let me define it first. So small x in a metric space, capital X with metric D, is a limit point, or sometimes called an accumulation point, of a subset Y of X if every open ball with small x as its center contains Y, a point of Y, other than X. The following, and I'm going to state some results here that without proof, but they relate to limit points. So this is sort of an alternate definition or equivalence. X is a limit point of a subset Y of a metric space if and only if there exists a sequence, an infinite sequence, such that the distance between an element in the sequence and X approaches 0 as I goes up to infinity. So in other words, as you move along this sequence here, the elements get closer to whatever the limit point in question is. And we also have this condition that none of these terms in the sequence equal X. And in which case we say that the sequence converges to X, or we can write it this way: the sequence converges to X. Excuse me. More technically, you can write it this way. This is sort of the limit notation from calculus. So for every epsilon greater than 0, there's some natural number capital N, so that every index, small n, bigger than that, capital N, when you take the difference, you're less than epsilon. That's saying the same thing as this. It's kind of complicated notation, but I thought I'd give it here just to be complete. So here we have an example. The point 0 is a limit point of this set. Even though it's not in the set, it's a limit point because these terms get closer and closer to 0, and you can you have basically this infinite sequence that approaches 0. So this fits the definition. What doesn't fit the definition of a limit point is the point 1. Since there's no sequence in here that's approaching 1, 1/2, 1/3, 1/4, none of the elements in the sequence are limit points. They are adherent to this set. 1 is adherent to this set because it's in the set. Remember, when we defined adherent, we said that the set of adherent points are all members of the set itself. So these isolated points are adherent, but they're not limit points. So we have another another theorem, I should say. The set of limit points for a subset Y of a metric space is a closed set. So if you take all of the limit points in a set, you'll get a closed set. And we can introduce this concept of equivalent metrics now that we've talked about convergence here. So two metrics, d sub 1, d sub 2, on a set X are equivalent if and only if the convergent sequences in under one matrix are the same as the convergent sequences in the other. So I have a problem for the listener. Let X with metric D be a metric space and define another metric on the same space. Here, D prime equals the minimum of 1 and the distance between X and Y. So whatever smaller you would take as the definition here. And then the problem is to show this is a D prime is a metric. So you need to show the 4 properties that we defined earlier in the first lesson on metric spaces. And then the harder part is to show that they're equivalent. And that, remember, we just defined equivalent in the previous slide. And once you show that, then we have the result that every metric space is equivalent to a bounded metric. A point X in a metric space is an isolated point of a subset Y of X if there is some R greater than 0 such that an open ball centered at X with radius R has as its intersection with Y only the set of the set including X itself. So the idea is that you can put a ball around little x and there would be no other points from Y in that open ball. And that would kind of be the obvious definition of how you would define isolated. So we have another result here related to isolated points and limit points that give us another definition for closure as well as by implication for closed set. So the closure of a subset Y in a metric space is the disjoint union of the limit points and the isolated points. So if you take all of the limit points, which may or may not be in this set Y, and all the isolated points, which are by definition in Y, then put those two together, you get the closure of Y. And if you have a set whose contains all its limit points and isolated points, then that would be a closed set. So I give an example here, and we take the disk, the closed disk, and then in union with the set of these 2 points which are outside of the disk. So these are isolated points. This set collectively is closed. All the points in the disk and its boundary are limit points, and then these are 2 isolated points which by definition a part of the set. So this set is closed. Then we also have something called the boundary of a subset Y of a metric space. It's defined to be the set of points adherent to both Y and the complement of Y. The complement are the points in X but not in Y. So the boundary of Y is denoted with this notation here. The following result, again stated without proof, effectively provides alternate definitions of open and closed sets of a metric space. So let's look at these two here. A subset Y is open if and only if the intersection between Y and its boundary is empty. So let's think about that for a second. So the intersection of Y with its boundary. So let's say we had, ignoring these points here for a second, let's say we had this disk and it didn't include its boundary. So the intersection of Y and its boundary is empty. That would be true. So because none of these points are included. A subset Y is closed if and only if its boundary is included in Y. So we see here if this set is not closed because the boundary of these points here, again ignoring these points for a second, these points here are not in Y. Now if we made this line solid and basically said that we're including the interior and the boundary here, then the boundary would be in Y, and we would include the we would conclude that this is a closed set. Now looking at this example here, I want to expand it to include these little points here, which I'll explain in a second. So let's say we have a disk including its interior but not its boundary, and then we have these points that are also part of the set. The black points are, and they converge to some red point here. Let's say that point is not in the set Y that we're talking about here. So how do we classify the various points in this set? Let's take one at a time. So we have the adherent points. So remember from before, every point in the set is adherent to it. So all of the gray would be adherent, and then these black points would also be adherent, and then the red point would also be adherent because every open ball about the red point would include one of these black points. As we said, they converge to the red point. So the red point, while it's not in our set in question here, it is an adherent point. It's also a limit point. Now none of these other black points are limit points because you can put a ball around any one of these and not include anything else from the set. In fact, these are isolated points. All these black points are isolated points. The red point is not an isolated point. The boundary of this set is the dashed line here. That would be the boundary. What about the red point here? Is that in the boundary? Let's see. A boundary is defined to be the set of points adherent to both Y and its complement. So yeah, I think this would be in the boundary because the red point, no matter whenever you encircle this, you are going to get some of these black points in it, and you're clearly going to get things in the complement of our set. So yeah, the red point is in the boundary, which is a little bit weird, right? Because it's not along with these other sets. It's kind of nestled in with the isolated points, but the red point would be in the boundary. So that's an example. I have some more words on how these concepts are related in the following slides. We'll talk a little bit more about that in a second. So a little bit more clarification. Some of these points I'm repeating myself, but I'm just saying things in different ways, hopefully to get the point across. So unlike adherent points, a limit point of a set in a metric space cannot be an isolated point. So we saw that in our example at the bottom of the last slide. So a limit point cannot be isolated. We know that because we have to have a set of points from a sequence of points from y that are getting closer and closer to our limit point. So the point itself can't be isolated. Adherent points include all points of a set y. We've said that before, including isolated points. Limit points exclude isolated points because the neighborhoods of an isolated point x can avoid other points of y. So again, I'm sort of repeating myself, but just saying it different ways. Every limit point of y is an adherent point of y, but not every adherent point is a limit point. And just one more time, saying almost the same thing. If x, little x is in y, some subset of our metric space y, x is isolated, and x is isolated, it is an adherent point, but not a limit point. Okay, so sorry for repeating myself. Hopefully, stating it in slightly different ways helps, and you may want to just make up your own example and convince yourself what are isolated points, what are limit points, what's in the boundary, what's in the closure, and so forth. And I would suggest doing something like the example I had in the previous slide with a disk. You can make it either open or closed, and then maybe have some isolated points, and then maybe some other isolated points in a sequence that converge to a point, and try to classify those points along these different categories that we have. So let's look at a few theorems. We have one here. The limit of a convergent sequence in a metric space is unique. So assume that we have a sequence x sub n that converges to two different points, x and y. We want to disprove this, of course. That's since the theorem says it should be unique. Then for each n, we have that the distance between these 2 points, x and y, is less than or equal to the distance from x to x sub n plus the distance from x sub n to y. That's from the triangle inequality. As n approaches infinity, the two terms on the right of the above inequality, so these two terms here, go to 0, which implies that the distance between x and y is 0. And then we know from the definition of a metric space that this is only true if x equals y. So that was pretty easy. We have another theorem. If y is a subset of a metric space x, then at point x, little x, in our metric space, capital X, is adherent to y if and only if there is a sequence in y that converges to x. So the if and f means we need to prove this in two different directions. If there exists a sequence in y that converges to x, then every open ball centered at x contains points of the sequence. So by definition, x is adherent to y. So that proves it in one direction. Going in the other direction, if x is adherent to y, then for each integer n greater than 1, there exists some point x sub n, an element of the open ball x with radius 1 over n, intersection with y. That's from the definition of adherent. And we're just selecting these radii 1 over n so that we can establish that there's a point in each one of these open balls intersected with y. Then the sequence x sub n is defined here, has the property that the distance between x and x sub n is less than 1 over n, and that approaches 0 as n approaches infinity, so x and x sub n converges to x. Let's look at another example. In this example, I want to illustrate some of the concepts we've talked about so far: limit point, boundary, closure, and so forth. So here's the example. We have a set Y that includes the unit closed disk with the points 0, 0, and 0, 1/2 removed. So we kind of punctured it in two places. And then we have this set here, 3, 0, 5/2, 0, 9/4, 0, and so forth. It keeps getting closer and closer to 2, 0. So these are all along the x-axis because y equals 0 in every case. And the limit as I goes to infinity is 2 of this part of the point. So we have that is the set. In other words, the unit disk, these 2 points removed, and then all these points here. So the set of adherent points, i.e. the closure, is the closed disk, x squared plus y squared less than or equal to 1. So we would these 2 points would be adherent. And then the limit point here of all these sequence, even though it's not in A, 2, 0 would be inherent because whatever closed ball we put around this, open ball we put around this, we're going to include some points from this set here. So since y does not equal its closure, y is not closed. The interior of y is the unit open disk, so we don't have the boundary in this case. That's not included in the interior. And also the points that we removed, 0, 0, and 0, 1/2, they're also not interior points. So, and none of these are either, none of the points in A. These are all isolated points, so they're not in the interior either. So y does not equal its interior, thus we know that y is not open. So y is neither open nor closed. The boundary of y is x squared plus y squared equals 1. In other words, the boundary of the unit disk is part of the boundary of y, and then you also have these 2 removed points. Even though they're not in y, they would be on the boundary. And then we have the limit point of this set A, 2, 0. That's also on the boundary because every open ball about this includes both points in A, which are in turn A is part of y, and points that are not in y. So this point is also on the boundary. And I mentioned this, all the points in A are isolated. And the point 2, and I also mentioned this, and the point 2, 0 is a limit point, as are all the points in the closed unit disk, including these 2 that even though we removed them from y, they're still limit points because there's clearly many sequences within y that converge on these 2 points. So let's look at the picture of this on the next slide. So here we have the diagram of what we were talking about on the last slide. We have the unit disk. The 2 little white things here are the points we removed. So they're, as we mentioned, they're not in the set, but they're limit points. They're also adherent to the set. Then we have this set of points here, this sequence. I couldn't draw them all, obviously, because there's an infinite number, but it goes 3, 2.5, 2.25, keeps getting closer to 2, and then 2 is not in the set, but it's the limit. So 2 is a limit point of well, the whole set here. It's also adherent, and it's also on the boundary. And then the other points, all these black points here, the infinite number of those, they're all isolated. Okay, so that's it looks similar to the rough picture I drew a few slides back, and I thought I would just do a second example to kind of reinforce some of these concepts. I know there's a lot of concepts here, and you need to kind of draw some examples and think about it. And keep in mind, we're just working in Euclidean 2 space here, but there's many other metric spaces where we could have similar examples that have boundaries and limit points and adherent points and isolated points and so forth. We have another theorem on this slide. So if Y is a subset of a metric space, then the closure Y is closed. In other words, the closure of the closure equals the closure of Y. And of course, if you did it again, you would come back to the closure Y yet again. The proof is reference 64 in my book. So if you download the book, you can just click on the link that's in the reference list, or you can go to YouTube directly, and you probably don't want to type that in, but that's the same link that's in my book. We need a couple of definitions from set theory for our following work in this lesson. These are not specific to metric spaces, but as I say, we need these for our work. So the first one is a complement of a set A is written as A with C here. And it's basically the elements in some universal set U, but not in A. So in the context of a metric space, this U would be our overall metric space, and then A would be a subset, and then C would be everything that's not in A, but in the metric space. So I have an example here. If you take the closed set 1, 3 in Euclidean one-dimensional space, then the complement is everything not in here, but in the set of real numbers. So you go from minus infinity to 1, not including 1, and then the union with starting from 3 to infinity, but not including 3. Then there's, excuse me, there's something called the relative complement of A with respect to B, and also known as the set difference between A and B, and it's written as B minus A, or sometimes B slash A. So that's a set of elements in B that are not in A. In terms of the universal set, we could write it this way here: A complement U slash A, or you could even write it as U minus A, but usually we'll just do A complement. So we have a set theory theorem here. This is really, again, this is really not specific to metric spaces, but we need this in some of our work, so I thought I would just remind the listener of this. So if you take A, complement the intersection of a collection of sets, B sub E, could be an infinite number, then this is the same as the union of A minus B sub E. If you take all these, so when you distribute A across the intersection, you get a union, and then you have the same thing, or almost the same thing, going the other way. If you have A minus the union of a collection of sets, and that equals the intersection of A minus B sub E. So these are basic set theory relationships. I have a proof for the first one here. Second one's similar. So if and just to keep in mind, when you want to prove something in set theory, you normally take an element of one side and show that it needs to be in the other side, and then take an element of this side and show it must be in that side. And then that proves that this is a subset of this, and then this is a subset of that, and of course that implies that the two are equal. So that's what we'll do here. We'll basically do it with a number of bidirectional statements, if and only if, so we don't have to go back and forth this way and then this way. So if X is an element of here, A minus the intersection of all these B's, that's true if and only if X is in A and not an element of this intersection. And that's true if and only if X is in A. Yes, we already had that. And then X not being in the intersection, what does that mean? It's not in every element in this set. So it just needs to not be in one of them, at least one of them. So that's why I wrote this here. X is not an element of B sub F, or at least one F in our indexing set E. And that's true if and only if X is an element of A minus BF. That's just kind of writing this in more formal language. So this means X is an element of this here. And that's true if and only if X is an element of the union, right? If it's in one of these, then it's in the union. So we come over to the other side. And again, I did if and only if all the way. So we've gone from here to here, and then we've effectively shown it that way, going the other direction, which means these two sets are equal. If you want to refresh your set theory memory, you may want to try the same thing with this second one. The proof is going to look pretty similar, and I would invite you to give that a try if you're a little rusty on your set theory. So we'll need to use these. That's why I could have just stated them, but because they're not really metric space things, but I thought as a reminder I would do it here. Open and close. So we have another theorem about open and close, and you can see now why I talked about the complement. A subset Y of a metric space is closed if and only if its complement is open. So that's interesting. So we recall from earlier examples, I mentioned that not being closed doesn't imply open, but there is a condition that relates to two, and that's complement. So the metric space is closed if its complement is open, and the metric space is open if its complement is closed. And you can take a look at the YouTube video for a proof. Same person here, the math sorcerer. That's not me, it's someone else. And if you go to the link in my, the reference in my book, you can just click on the link there, or if you can type this in. You probably don't want to do that. So I would suggest going to the electronic version of my book and then just cut and pasting that link and using that to get to your to this proof if you're interested. The intersection of any collection of closed sets is closed. That would include infinite collections. And the union of any finite collection of closed sets is closed. If you recall from our last lesson on open sets, we had almost the opposite of this. And in fact, I need one of those theorems from the previous lesson, but I wrote it down here. Any union of open sets is an open set. And then we had the other theorem saying any finite intersection of open sets is open. So the role of open and closed and union and intersection are shifted here for closed sets. So let's prove the first part. Here we have a metric space X and our closed sets, Y sub A, where A is in an indexing set, capital A, which could be finite or infinite. Let that be our collection of closed sets. Then by theorem 71, we have X minus the intersection of all these sets equals the union of X minus each individual set from our collection. And since each one of these Y sub A is closed by our assumption, then each x minus y sub a is open. That was the theorem from the previous slide. Then by theorem 64, which I've written down here, the union of all these guys is open. And so since this equals this, we have x minus the intersection of the y sub a is open. And then since this is open, the complement of this is closed, which is the intersection of all the YAs, which is what we wanted to show. So the second part is similar. You need to use some of these. You're going to need to use the some of these previous theorems, as well as I believe it will be theorem 65 concerning the intersection of open sets. But it follows very similar to the proof here. So you might want to test your understanding of some of the concepts by taking a shot at the second part of the proof. On this slide, I have an example of an infinite intersection of closed sets and an infinite union of closed sets. Let's look at the first one. If we take the sequence of sets in a one-dimensional Euclidean space, y sub n, then we have, defining it this way here, the first element is minus 1, then 2, and plus 1, it's 3. You put in, say, 10, you get minus 1/10, and here you would get 2 1/10. So this side of the left side of the closed interval here is approaching 0, and the right side is approaching 2. If you take the intersection, every one of these sets includes 0 and 2. And in fact, that's the only thing in the intersection. So the intersection of the y sub n's, all of which are closed, equals a closed set, which is what we would expect from the theorem on the previous slide. Excuse me. And the second example is the more interesting one. You have z sub n equals the intervals 1 over n, and then this formula here, 2 to the n plus 1 minus 1 over 2 to the n. And I wrote out a few of the terms here. You notice you have 1. Let's just look at the first element here, 1, 1/2, 1/3, 1/4. So this is getting smaller and smaller. You're approaching 0. And then on the other coordinate here, 3, you have, if you put in 1, you get 3/2, 7/4, 5 over 8. So this is approaching 31 over 16. This is approaching 2. So you never actually include 2 because it's only in the limit that you have 2 here, but you're getting closer and closer to 2. And then this this sequence here, 1, 1/2, 1/3, that approaches 0, but it never actually includes the point 0. So the union of all these is the interval from 0 to 2. And as we see, it's an open set. So, and again, we would have expected that from the theorem on the previous slide, that the union of an infinite number of closed sets does not necessarily need, it could be closed in some cases, but it doesn't have to be. And we've seen here where that happens, it becomes an open set when we take the union of all these. We have a theorem here, the complement of a one-point set in a metric space, where the metric space consists of more than one point. This one-point set is open. So let P be our one-point set, and we want to show that the complement of P in the context of X is open. Choose any point X, an element of the complement of P. And we know that X doesn't equal P since X has more than one point. And that implies that the distance from X to P is greater than 0. So we let R equal half of this distance and consider an open ball centered at X with radius R. And if we can show that this open ball is a subset of the complement of P, then we're done. We're basically showing that x is an interior point of the complement, and since x is any point in the complement of P, that would imply that all the points in the complement of P are interior points, which means that the complement of P is open. So let's prove that. We take any point y in here, and we want to show that it's in the complement of P. We first note that the distance from x to y is less than r. That's because if y is in here, everything in this ball is a distance less than r. Then we use the triangle inequality. The distance from x to p is less than or equal to the distance from x to y plus the distance from y to p. And then we subtract this distance from x to y from the distance from x to p, and we get this here. And since the distance from x to y is less than r, where r is equal to the distance from x to p divided by 2, we can substitute this in here. We're basically, if this is greater than this term minus this term, and we put in something smaller here, this is still greater than this. And of course, when you subtract this, you get this here. So we get the distance from y to p is greater than the distance from x to p divided by 2. So the distance from y to p is greater than 0, meaning that the y could not equal p. That's just from the definition of a metric space. And so that means if y is not equal to p, y is in the complement of p, which means that since y was any where were we here? Since y was any element from the ball, the open ball here, that means this open ball is a subset of this, and that's what we set out to prove. Okay, so that's the end of this lesson. We'll have some other concepts related to metric spaces, which we'll cover in the following lessons.